and at the top is Karsten. So let's see. Let's just go this way. Okay, there's the title of my talk. It's actually going to be in two parts. So there's the first part. You can see it'll be on the Woodford Shale. I changed the order once I saw that it suggested that maybe we do a specific Woodford following Pat's overview. And then I'm going to do a talk on the Flower Pot Shale. Actually, Ken Johnson could probably come up and give this talk because I lean very heavily on Circular 77 that came out in 76. And interestingly, people leave piles of books when they clear their office. So I was actually in Sarkey's Energy Center, and there was Circular 77. I saw it sitting there, and it was like, copper deposits in Southwest Oklahoma. And I thought, wow, that's kind of interesting. I don't know much about it. And it was, the binding was already coming off, the glue on the back, but it was interesting. So I started reading about it, and then Carl asked me if I'd give a talk. I said, okay. And then we got this Woodford data. So my apologies for being, and I'll just get busy because I will try to be brief and to the point. I'd like to acknowledge OGS Nick Heyman. We got to talking, and he said, my spouse gives me about a $10,000 a year analytical budget for my research. So when talking with Nick, he said, well, actually, this phosphate, these rare earths, I think the OGS can free up some money to pay for these. So the analytical work for that was done at ALS in Reno. And Carl Simcox and David Hull, who are here, were field partners. David knows a lot about the oceanic anoxic events. He's also an excellent sequence stratigrapher. So when I had questions, I called him, and Carl is an all-around bright guy, but and also a phenomenal geochemist. So when I had geochemistry questions, I called Carl, and eventually we all ended up going out in the field together at various times. So there's a Woodford phosphate nodule. And I'll go through all this, and eventually I'm going to show you a little prospect up on the Lawrence Uplift, about 4 miles south of Ada. So we've kind of covered rare earth elements and their uses, widespread, everything from earphones and speakers to energy efficient light bulbs. And if we look at some of the key elements in terms of their critical supply versus their importance to clean energy, we can see this mid to heavy rare earths in the neodymium, dysprosium, terbium range as being very critical to understand and source. But if we take the usable rare earths and kind of look at it, what's really critical, wind turbines, magnets, hybrid vehicles, defense, and really our smartphones, because let's face it, none of us could live without them now, as much as I hate it. So I saw this, China's a rare earth monopoly diminishing. They show global mine production in tons. So notice the kind of mauve wedge in Myanmar. Well, okay, let's just consider that part of the Chinese production. This is the nature of the geopolitics in the world. However, it's not just mining. We have to bear in mind most of the stuff gets sent to China to be smelted. The ore concentrates from Mountain Pass and Australia are sent to China, smelted and re-exported. So the Chinese dominate and control the market still. The rares are interesting. They have this lanthanide contraction. They have an outer shell that fills first, and then the inner F shell fills up, and it leads to this ionic contraction. Importantly, because they have similar chemical properties, if you find rare earths, you generally find at least some of them all together. It also means that they're difficult to separate out into their individual components and turn into high purity elements. There are about 10 rare earth bearing minerals, but in the sedimentary environment, various forms of apatite is the dominant rare earth bearing mineral. And apatites are forming from direct precipitation from seawater. There's 3 kinds of apatite: chlorapatite, fluorapatite, hydroxyapatite. And it's the substitution of these rare earths in +3 for sodium and calcium and for phosphorus that lead to their incorporation into the crystal lattice in phosphate nodules. Most of the global recovery rare earths is the byproduct of mining operations. But the separation of them into the components is difficult and often requires somewhat aggressive geochemical techniques. However, apatite is relatively soluble in sulfuric and phosphoric acids, so they're relatively easily leached, and recoveries are easily exceed 60%. And we heard from Pat, sometimes up to 90%. The Woodford Shale was deposited on a south-facing rifted margin on the subducting Laurentian plate during closure of the Rayek Sea. It's a late Devonian, organic, rich, silicious black shale. It's correlative to the Chattanooga and New Albany. The Chattanooga and New Albany also have nice phosphate nodules. The Arkansas novaculite is its down dip deep water equivalent. It spans two mass extinctions, the Franian-Flaminian, the Devonian Carboniferous. My interest in the Woodford actually is related to these mass extinctions, looking at mercury and the input of mercury and methylmercury from volcanic eruptions as a poisoning mechanism to drive these mass extinctions. Particularly, we see it strong evidence at the Devonian Carboniferous boundary. And that's some research I'm conducting with some Michael Rakosinski at the University of Warsaw in Poland. And fascinating time this was deposited during the rise of land plants. And we can see there on the right-hand side, there's the deep water Arkansas novaculite. And we'll take at least one slide, take a look at that. It's a world-class algal rich source rock. These slides have been modified. They're Cardot and Comer. I'd like to acknowledge also the work that Roger Slatt and his students did as well in establishing a lot of the sequence stratigraphy in the Woodford. The upper Woodford, there's this little, so I don't have a pointer, but a little star thing. That's we see a lot of. That's where the phosphate nodules are concentrated. We're going to take just a quick geographic tour. We're going to start on the Lawrence Uplift. The town of Ada is about 50 miles as the crow flies. And we're going to go basically on a deepening transect into what would be paleo deeper water depths through the Arbuckle Mountains into the Ardmore-Marietta Basin. And we'll actually cross over into Texas and look at some core that Richard Brito worked on. And then we'll also look at just quickly at the Arkansas novaculite. But what we see is that the nodules occur, they're concentrated, once again, in these little blue things up at the top. There's at least 300 miles, if you restore all of this, that the phosphates are being deposited at the upper Woodford. And it's almost an event that occurs. Here's on the Lawrence Uplift, on the slides on the right are from the Weish Quarry. The upper one, you can see interesting variations in habit from spherical to elliptical, and there's some kind of wispy beds. One of my favorites is the lower left. Here's a pyrite nodule. You see the concentric zoning, and it's got this pyrite bed that's compacting around it. Now, the geochemistry of these eugenic muds and phosphate precipitation is a fascinating topic that I don't know much about, but is worthy of study. And you can see here Carl's collected some nodules and broke them open, this beautiful concentric banding. And as you move to the west from the Weish Quarry, W Quarry, in outcrop along County Road 1610, there are abundant phosphate nodules in outcrop. So at or near surface, there's abundant phosphate. So we go to the north and south limbs of the Arbuckle anticline. The north limb on the right-hand side, it's interesting, Patrick mentioned some of these nodule lags in conformity. Look, these are just packed, and I think there's a disconformity to unconformity at the top of the Woodford. And there the nodules are really concentrated and you have this clay infiltration. But you can see they're spherical to oblate and fairly elliptical. And you go to the south limb on I-35, and we start to see more spherical oriented nodules. And we see once again this very nice banding on the lower left-hand photograph. Going even further down dip in the Ardmore Basin, so the McAllister Cemetery Quarry, there's abundant phosphate nodules there. They all tend to be round. On the upper Woodford there is just packed with them. And lastly, as you cross over into Grayson County, Richard Brito's thesis included a study of core by Jetta Operating Company. And you can see the stick log with the gold circles or the phosphate nodules that were observed in core. And circled up there, you can see in blue circles are the phosphate examples. And the handheld XRF, you can see a few spikes associated with this in the phosphate shown in purple text. If we were to go stratigraphically down dip and restore, and this would be now hundreds of miles, you've got to take out movement on the Choctaw Fault, right, and restore the Arkansas novaculite. Here we are at Scratch Hill. There's conodont data, and I found it very interesting that this is about the Franian-Fominian boundary. So we see phosphate, we saw the phosphate nodules there elsewhere at this boundary, but as you move up into the section onto the shelf, we see them at the Devonian Carboniferous boundary. So I think it's really I'm really excited about Patrick's talk. So there's been 3 studies by Asai, Kirkland, and Boardman that looked at these nodules. They're composed of fluoroapatite. They're precipitated at or near the seafloor under anoxic conditions. The phosphorus source was probably released by anaerobic decay of phytoplankton that settled through the water column. The nodules commonly contain radial area test and sponge spicules. There's a diverse morphology and internal variations, and they show geographic trends that we saw in those photographs. Spherical, concentric, well-organized nodules are prevalent down dip, the I-35 South and McAllister Cemetery quarry. As you move up depositional dip, they tend to become more oblate and elliptical. Spherical nodules do occur, and the up dip ones have less commonly this internal organization. And Boardman, the lower left, you can see his classification. He did some laser ablation ICP-MS, and the dark bands are associated with higher metal content, such as vanadium. It suggests that redox conditions or possibly supply of metals were varying during precipitation of the nodules as they grew. So here are the rare earths that we collected. It's really, I'll admit, this is incredibly undersampled to us. So I collected 3 nodules, just so I could not have to draw a line between 2 points from 4 different locations. Interestingly, at the top, we can see this is from the Weish Quarry up on the Lawrence Uplift. Total rare earths, 1,200 ppm. That's respectable enrichment total. I've normalized to the post-Archean shale. If we do North American, I think it's about 1.25 difference. It's not a big difference, the normalization factor. In orange, you see as you come down dip, that's the I-35 North. And you move further and further to the south, we see this progressive decrease in the enrichment of rare earths as we go basinward. So that's an indication. I'm waiting right now for ALS to get back with more analytical work, but it's very interesting that we see the rare earth concentration change from north to south, and is coincident with the change in nodule morphology, stratigraphy, and organization. So there's the Lawrence Uplift, a cross section from Billham, great Billham. Anyway, it's relatively shallow. There's a simple structure. It's shaded in blue, the upper right-hand map. There's about a 2 square mile area with Woodford at or near the surface. There's the average enrichment. Neodymium averages for the 3 samples, 249. And monetarily, neodymium is probably the one to go after because it's higher concentration. And its price fluctuates from in the last year from $8 to $4. It's also enriched in dysprosium. So that's pretty nice. There's an active quarry. And there's an example on the quarry wall, and it's quite extensive. You can walk around the quarry wall and see these. There's a bit actually of evidence that we see a vertical succession, Walther's law, of spherical nodules to oblate nodules to wispy beds. There's a barren bed in the middle, and then we see this succession of change in morphology going up, as if what we see laterally is taking place vertically. Quite fascinating. There was a core taken behind the quarry wall, sponsored by Devon and studied extensively at the University of Oklahoma. And we can see here in blue and green, the band across there, that's about the base of the quarry, marked in the upper Woodford. And in purple, the big ppm, that's the phosphate in handheld XRF. The core did have phosphate nodules. And that interval is about 70 to 75 feet thick. And I'll just highlight this, and this is from the MSBO paper that Patrick was second author on, that there are secular variations in rare earth content. And the Devonian is one of the intervals that seems to be favorable for enrichment in rare earths on a secular basis. The core element is 21 meters. It covers 1,280 acres. There's already an active quarry. This looks like a relatively simple structure. I think it's a favorable place to think about maybe a rare earth development. And I'll just say back of the envelope calculation, dare I say it, I think there's at least $200 million of neodymium sitting in those 2 square miles. Now, whether it's economic or not is another matter. So in conclusion, the Woodford phosphate nodules show spatial enrichment in rare earths. The updip areas are more enriched in rare earths, apparently. The Lawrence uplift shows the strongest rare earth enrichment. Its simple structure, minimal overburden are favorable for strip mining, and further appraisal is underway to assess its commerciality. So key references. Part 2, let's shift gears. Thank you, Ken. You know, he could give this talk. But anyway, we're going to go now to Southwest Oklahoma, the Permian flower pot shale. If you've ever been out there, it is no country for agoraphobic old men. Cobalt production. It's kind of interesting that there's a lot of cobalt mines that are associated mostly with ultramafic rocks and weathered ultramafic rocks. But the dominant cobalt production in the world is in the stratiform copper deposits and associated cobalt in the so-called Democratic Republic of Congo. Cobalt's a critical mineral for batteries. It's essential to the economic and national security. The biggest deposit, 71% of the world's copper and cobalt reserves. Cobalt reserves are the copper mines in the Central African copper belt. The flower pot shale hosts stratiform copper deposits. So let's consider the cobalt potential in the flower pot shale in the Creta mine in Jackson County, Oklahoma. Cobalt's a transition metal and often occurs with iron and sulfur, replacing in pyrite. The nickel ores are usually massive sulfides, and importantly, cobalt ores must be smelted to produce usable metal. They go into lithium-ion batteries, metal alloys for turbines, prosthetic limbs, as well as catalysts for pigments and coloring. This is why I went into the oil business. I value stability. On the lower right-hand side is the price of cobalt over the last 60 years. Anyway, because it's so concentrated in Zaire, formerly Zaire, civil war, civil unrest affects the price. 480% swings in price. The last few swings were actually related to China stockpiling cobalt and then releasing it. So the ability to manipulate the market is tremendous and poses an economic risk for anybody entering the mining business. And we see kind of the effect of the rise in battery technology, the plunge from COVID. Current spot price is now $52,000 per ton. So just briefly, the Central African Copper Belt, this is work that was done, presented by the USGS. The cobalt grades are rich enough actually to reach primary production at several mines if it's greater than 0.68% cobalt. But even the other copper mines, some of them carry greater than 0.1%, makes it economically attractive. The mineralogy and paragenesis is complex. But it often results from replacement of pyrite. And the sulfur isotopes indicate that this is related to sulfate reduction and the precipitation of pyrite. There's really two distinct belts, the Congo copper belt and the Zambian copper belt. The Congo copper belt has more deposits, but fewer giants. In the Zambian copper belt, it's interesting that the deposits are actually associated with mafic rocks on the western side of the belt. Thank you, Ken, for this picture, back when you could actually find ore at the surface of the Creta mine. So let's look at, this is a chalcocite-bearing shale at the Creta mine. There's copper-bearing Permo-Triassic sediments in Oklahoma at multiple places, and they're relatively widespread. Chalcocite is probably the primary ore, but where oxidized, the malachite and chalcocite are found together. There are some trends in copper mineralization that extend up from across the Red River from Texas. In Cimarron County, northwest Oklahoma, Colorado, and New Mexico, in the Sheep Pen Triassic sandstone, there's mineralization of copper, gold, and it's associated with some interesting breccia pipes that had pretty good ore grades, but they've largely been mined out around the turn of the century. 40 miles south of here, there's a very interesting copper deposit. It's a roll front in the Wellington group, and actually carried up to average 4 ounces of silver per ton. That was also a turn of the century. It was evaluated and drilled and trenched in the 70s. There's a nice report on it that's available. And the Creta mine in Jackson County was mined strictly for copper, an average 2.3 weight% copper. And you can see it sits in the San Angelo Trend, and I'll draw attention north of there, about 15 miles, is the Mangum deposit. And we'll briefly look at both of those. There's the Creta mine. Once again, thank you, Ken. I told you he could give this talk. He was there when the mine was active. So it has a great aerial view of the mine. You can see this bucket in the mining. They strip mined this out. It was active and operated by Eagle Pitcher from 64 to 75. About 2 million tons of copper ore was stripped from a copper-bearing shale. They had an on-site mill to concentrate the ore, and it was railroaded to El Paso to an Asarco smelter. The Mangum deposit, 15 miles north of Creta, has never been developed. It occurs in the Flower Pot Shale, actually the lower part of the Flower Pot Shale, and we can see it kind of color-coded, generally associated with more darker colored gray shales with some red beds in between. And there are actually a couple of different units that are the copper-bearing shales. The Flower Pot Shale is Permian, Guadalupean in age, and it was deposited in brackish water in restricted marine embayment on the east side of the Permian Basin. The Prewitt Shale is the copper-bearing shale at the Creta mine. And the copper occurs as chalcocite as both disseminated grains, replacement of pyrite, and replacement of pollen spores. Sulfur isotopes indicate the chalcocite was formed by bacterial reduction of sulfate, and the gypsum was precipitated from Permian seawater. Recall, the African copper belt deposits are also associated with bacterial reduction of sulfate. So there's some commonality. There's a cross-section showing the Meadows Prewitt Shale and the Meadows Shale at Mangum up to the north. And I've kind of charted this up to color code the presence of more oxidized greenish ore at the Meadows Shale. The Meadows deposit is thicker, but it has half the grade. Notice the units here. The Creta mine operated for 15, 20 years at an 8-inch bed. So it's pretty amazing when you think about it, an 8-inch bed being economic. But if you get your operations down and you have efficient milling and favorable prices, thin things can work. I believe the copper at the Creta mine was probably sourced from the mafic and ultramafic rocks from the Cambrian Age Raggedy Mountain group. We see in the Raggedy Mountain group, there are some limited prospect pits. The Hale pit, as a pegmatite dike, was mined for chalcopyrite and cuprite. And there's enough geochemical data from studies done I'll just give a shout out to Charles Gilbert and his cohorts. But you can see the copper and cobalt numbers in the Raggedy Mountain group. So we see the two elements exposed there, and that's likely the source, unproven. What's the cobalt potential? Well, there's the key analysis, and this is from Lockwood's PhD, as well as his paper in Memoir 76 that Ken Johnson organized a workshop, and there's a series of papers in there. You can see the copper oxides there, and what I did was I took the gray, red, and maroon shales and separated them out and averaged them to separate them out from the copper-bearing shales. You can see the cobalt numbers shaded in light blue, coming across from Cretan and Mangum to 19, 20 ppm and 22 ppm. So what does this really mean? Unfortunately, if you look at this relative to the African deposits, 0.1% would be nice. 0.002 weight percent and 0.0024 weight percent does not cut it. It's not even close. There are some interesting aspects in terms of enrichment factors. If we just consider the geochemistry of the system, that the Creta copper shales are depleted in cobalt relative to the other shales. And only the red shales actually show any cobalt enrichment. The situation is slightly different at the Mangum prospect, where the copper shales are slightly enriched in copper and vanadium. And the gray shales are enriched in all elements. And the red shales show slight cobalt enrichment. This would be an interesting study for those interested in, I think, Permian ocean chemistry and variations. I think the data are available out there. So the Creta mine shut down in 1975, owing to low copper prices and increased smelting costs and regulations. The Asarco smelter now is in receivership to the EPA, and it's considered a Superfund site. Not so much from the copper smelter, but from the zinc smelter. But it was considered one of the larger environmental bankruptcies that occurred when after Grupo Mexico bought it and sold it off. However, although it lacks cobalt potential, is it considering worth the copper in the Creta mine, considering even at today's prices and projected to go higher? They're 670% higher than when the Creta mine was active. There are enough published maps in Memoir 77, so I've kind of layered things up. The outline in bright and kind of green in the middle is the outline of the mine. There's in the white square is the mill. The orange outlined in red is what would be 0.5% greater than 6 inches. So kind of the sweet spot. The other ore grade, lower ore grade is in pink. And also highlighted in gray and with the black line is the greater than 40-foot overburden. And you can see that these isopachs are quite nice in layering up and showing the ore grade and overburden thickness. And there's a cross section that shows that the overburden thickens relatively rapid to the west. And that means that the unmined ore that's left, the richer, is under thicker overburden, which would have a potentially negative impact on economics. So in conclusion, Creta holds no cobalt potential. For copper, thicker overburden is a negative factor. Notice the mismatch, and it should be factored, but I had longer distance for ore shipping, but I was told by my friend Sterling Cook that he's a copper geologist, that once you get it on a train, it doesn't matter if it goes 50 miles or 1,000 miles. It's getting it on the train to get it to the smelter. So I had to take that out. Creta might have remaining copper deposits at current ore prices. The abandoned Creta mine still holds mysteries. This is what Carl and I found. Who built the Creta cannon? It's you can go out there and see it. And look at the bowling balls, and they call it the one-eyed, one-barrel flying pumpkin chucker, defending our southern border from redbacks. So thank you, and really special acknowledgement to Ken Johnson Oklahoma legend by the Oklahoma Foundation, more than 60 years of sustained research on Oklahoma's geology with an emphasis on the Permian system. And he's still publishing and teaching. And I can think of nothing better than to have an OGS give an annual award in Ken's name. Thank you very much.